The remainder or factor theorem is a fairly straightforward kind of concept, really, and it brings together some of the things we've been looking at so far in the course. So I'm going to take you back to the polynomial that we had a look at a couple of videos ago, which is p of x equals x squared plus 5x plus 6. It's a polynomial function. We know that it can be factorized into x plus 3 times x plus 2. What happens if I set that polynomial equal to 0? Then the solution will be x equals negative 3 or x equals negative 2. So this is because this polynomial can be factorized exactly into these two factors. And then the null factor law takes care of coming up with two exact solutions. Well, if we draw these facts together, if I substitute negative 3 for x in the polynomial, I'll get negative 3 squared plus 5 times negative 3 plus 6 without drawing too much work into it. I've got 9 here, minus 15 is negative 6, plus 6 is equal to 0. And that's exactly how it should be. If it's a factor, or if it can be factorized, then x plus 3 must be a solution. Therefore, x equals minus 3 must work. Okay, similarly, p of negative 2 will give me the same thing. Negative 2 squared plus 5 times negative 2 plus 6 is equal to 0, because negative 2 squared is 4, 5 times negative 2 is negative 10, 4 minus 10 is minus 6, plus 6 is equal to 0. So we've got there again. Okay, I'm going to zoom out now because we're going to have a look at the first part of the factor theorem. And that is that if x minus a is a factor of p of x, then it must follow that p of a is equal to 0. X minus a is a factor of p of x. There's that funny old if with two f's in it again. Remember, it's not a spelling mistake. It means if and only if, and it means it works both ways, if that kind of makes sense. So if p of a is equal to 0, then x minus a must be a factor. And if x minus a is a factor, then p of a must be equal to 0. And we see over here on the left-hand side two examples of where we can see that's true. X plus 3 is a factor, x plus 2 is a factor, p of minus 3 equals 0, p of minus 2 is equal to 0. Now have a look at what I've got underneath there. I'll just put little dotted lines to separate it out a bit. This time I've got that other that other polynomial that we looked at 2 videos ago, and that is x squared plus 5x plus 7. And we know that if we divided x squared plus 5x plus 7 by x plus 3, we got x plus 2 as the factor, but a remainder of 1. Okay, so if I put in p of minus 3 here, then this bit here is going to be equal to 0. So this whole thing here is going to be equal to 0. And so I'm just going to be left with 1. Similarly with p of minus 2, I'm going to be left with 1 as well. Similarly, if I take the original, I'll get p of minus 3 is equal to minus 3 squared plus 5 times minus 3 plus 7. And that is equal to minus 3 squared is positive 9. 5 times minus 3 is negative 15. So that leaves me with negative 6. Negative 6 plus 7 is equal to 1. Unsurprisingly, because it's all exactly the same thing, this also gives me the remainder. Remainder, 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 remainder. In a similar fashion, p of minus 2 is minus 2 squared plus 5 times minus 2 plus 7, which is equal to 4 minus 10, which is minus 6, plus 7 is equal to 1. So what does that mean? It means that when I substitute a value into the function, if I get 0, then x minus that value must be a factor. If I get anything else, it must be the remainder. So if x minus a is divided into P of X, then P of A is the remainder. It's in fact the same theorem really, because we know that a remainder of 0 means it goes in evenly, and if it goes in evenly, it's a factor. So it really is the same theorem. Okay, so when x minus a is divided into P of X, then P of A is the remainder. If the remainder is 0, then it's also a factor. Okay, so that's basically it for the factor theorem and the remainder theorem. And what it can be used is, it's a powerful method for finding factors of polynomials, particularly of degree 3 or higher, without having to use complex kinds of rules and stuff in order to get there. So if we have a look at slide 15 here, there's an example, and I'm going to finish on this example. It's a pretty common one. Without dividing, show that x plus 1 is a factor of x cubed minus 2x squared minus x plus 2. So you don't have to divide in, you simply have to go like this. Look at what you're dividing by and reverse the sign of this bit here, x plus 1. So we go p of minus 1, and then we substitute in minus 1 cubed minus 2 times minus 1 squared minus minus 1 plus 2. And then we just need to confirm. Minus 1 cubed is minus 1. Minus 1 squared is 1 minus 2. So we've got minus 1 minus 2 is minus 3. Minus 3 minus minus 1 is minus 2. Minus 2 plus 2 is equal to 0. Therefore, x plus 1 is a factor. Done. Now this next bit says in slide 16, hence factorize the polynomial. Now you can use your polynomial division to finish factorizing it. Okay, so it's a degree 3 polynomial. So we need 3 boxes along and 2 boxes across with x plus 1. It starts with an x cubed, so that's what we'll put here. X times what equals x cubed? X squared. X squared times 1 is x squared. Okay, what am I looking for? I'm looking for a minus 2x squared. So to get to minus 2x squared, I'm going to have to take away 3x squared here. X squared minus 3x squared is minus 2x squared. Sometimes I like to do this to remind myself of what I'm sort of aiming for. This is going to be minus x. So I keep on going through those. So x times what equals minus 3x squared? The answer is minus 3x. I'm rushing this one, but you can pause and just think about it yourself. Minus 3x times 1 is minus 3x. I'm aiming for minus x here, so minus 3x. I'm going to have to add 2x to get to the minus 3x. And I've got x times what equals 2x? Well, it's going to be plus 2. And then I've got 2 times 1 is equal to positive 2. And if I check, I can see that this is indeed the same as this. If it was something different, then I know that I've stuffed up somewhere. Either x plus 1 isn't a factor and I've stuffed up, or there's a stuff up in my box method. What does that leave me with, though? It leaves me with p of x equaling x plus 1, the factor that I worked out, and then I've got x squared minus 3x plus 2. Then what you need to do is just check this out and say, is there anything else I can do to factorize it? And the answer is yes. Again, you can think about it, pause it, work it out whichever way you want to, but I'm just going to go straight to it. Pause if you want to. I can see that this is minus 2 times minus 1 will give me positive 2, and minus 2 times plus minus 1 gives me minus 3. So I can now just use my straightforward trinomial factorization to say this is x plus 1, x minus 1, x minus 2. And now it's fully factorized.